In special relativity, the standard rule for time dilation is straightforward. The faster an object moves through space, the slower it moves through time. Look at the standard Lorentz factor. This curve shows that bringing proper time to a complete standstill requires a constant velocity, asymptotically approaching the speed of light. But this model relies on an often overlooked constraint. It assumes constant velocity and ignores the temporal effects of a frame undergoing continuous acceleration. In 2011, physicist Arne Bergström published an analysis of hyperbolic spacetime motion that bypassed this absolute lightspeed threshold. Bergström demonstrated that proper time can be brought to a complete standstill without coming anywhere near the speed of light. His proof relies on a maximum velocity of exactly 0.25, or just 25% the speed of light. This plot compares two distinct paths to that same velocity. On the right, a trajectory achieving 25% light speed via standard constant velocity. On the left, reaching that exact speed through a specific hyperbolic acceleration profile. Following the straight path of constant velocity yields a mathematically negligible time dilation of roughly 3%. Moving along the curved hyperbolic transit to the exact same velocity yields 100% time dilation. Time effectively freezes. The acceleration profile of a co-moving frame provides a mechanism for time dilation that is independent of absolute velocity. To prove how this works, we must translate the algebra into geometry using a Minkowski spacetime diagram. We start with a stationary baseline reference frame, plotting time vertically and space horizontally. This diagram displays the space-time world line of a test particle subjected to a constant proper acceleration from a starting point, x0. The physical action of that continuous acceleration traces a distinct geometric hyperbola, defined algebraically as x squared minus tau squared equals x0 squared. Now, we shift our perspective from the stationary observer to the particle's own co-moving inertial frame. As the particle's relative velocity increases along the curve, its local coordinate axes do not remain static. Successive Lorentz transformations force both the spatial and temporal axes to continuously tilt inward, angling toward the 45-degree light cone. There are two separate mechanisms happening simultaneously here. The particle is physically advancing along the spatial curve, and its mathematical coordinate frame is geometrically rotating. During standard accelerated motion, physical acceleration and geometric frame tilting operate at distinctly different rates. Identifying the conditions for zero aging requires mapping exactly how the physical progression of the object races against the geometric rotation of its reference frame. How do physicists accurately map the actual passage of proper time experienced by the accelerating object? The solution is a Minkowski parallelogram. This construction calculates the exact time interval between successive points on an accelerating world line. This graphic breaks down the construction. We select a starting point on the hyperbola, labeled O, and build out vertices P, Q, and R. The first side, OP, is drawn along the tangent to the hyperbola. This represents the precise direction of the co-moving time axis. By adding 45-degree light cone help lines, we establish the boundaries and close the shape with the remaining three sides. Under a standard constant proper acceleration profile, the resulting parallelogram has a distinct open geometry. Looking at the completed shape, the tilted short sides represent the passage of proper time in the moving frame. These sides remain elongated because the relativistic tilting of the spatial axis is too slow to keep pace with the object's physical spatial acceleration. Because the tilting has not caught up to the physical motion, the object continues to age as it traverses the curve. Clocks run slower during standard hyperbolic motion, but the presence of a measurable short side in the geometry ensures that proper time continues to pass. We can alter this geometry. By modifying the hyperbolic acceleration profile, we can deliberately increase the speed of the frame's relativistic axial tilt. This chart shows the immediate geometric result of a steeper acceleration profile. The entire parallelogram compresses, narrowing the temporal gap. The increased acceleration causes the relativistic rotation of the axes to catch up with the particle's physical motion through space. To bring time to a complete stop, the velocity must adhere to a specific mathematical function. Velocity equals time divided by space. This velocity function shifts the hyperbolic asymptotes so that they intersect exactly at the spacetime origin. When the acceleration reaches this critical threshold, the geometry collapses. The parallelogram degenerates into a single double line pointing directly at the origin. The tilted temporal side has shrunk to a length of exactly 0. No proper time is passing in the moving frame. This diagram plots the geometry at two different velocities along the curve, 20% and 60% the speed of light. The state of frozen time persists across the entire trajectory. While physicists typically look for zero aging only at the speed of light, this geometric collapse is valid even at moderate velocities. By tuning the acceleration to precisely match the rate of relativistic frame rotation, the object enters a state of zero aging. The geometric proof is decisive, but requires verification through the foundational calculus of Lorentz transformations. Methodical. This equation calculates time intervals in moving frames. The change in proper time equals the change in stationary time, divided by the square root of 1 minus velocity squared, multiplied by 1 minus the spatial coordinate times proper acceleration. Under conditions of constant velocity, the spatial increments between time steps perfectly cancel each other out. But because velocity is actively changing during hyperbolic motion, those spatial increments survive the calculation and remain in the equation. The critical mechanism is isolated in that final algebraic multiplier, 1 minus space times acceleration. If the proper acceleration is tuned to equal exactly the inverse of the spatial coordinate, this specific multiplier instantly drops to 0. Because it is a multiplier, the entire calculation for the passage of time zeroes out, regardless of the magnitude of the velocity. Introductory models ignore this term, relying solely on the Lorentz factor denominator to drive time dilation toward infinity. Factoring in variable acceleration proves that perfect temporal suspension occurs far below the speed of light. The state of frozen time is a navigable geometric equilibrium in Minkowski spacetime, achievable at velocities far below the speed of light.